So, today we're going to try to read this tech blog from Netflix, Mount Mayhem at Netflix Scaling Containers on Modern CPUs. Imagine this. You click play on Netflix on a Friday night, and behind the scenes, hundreds of containers spring into action in a few seconds to answer your call. At Netflix, scaling containers efficiently is critical to delivering a seamless streaming experience to millions of members worldwide. To keep up with responsiveness at this scale, we modernized our container runtime only to hit a surprising bottleneck: the CPU architecture itself. Let us walk you through the story of how we diagnosed the problem and what we learned about scaling containers at a hardware level. Hmm, scaling containers at a hardware level. This is interesting. The problem: when application demand requires that we scale up our servers, we get a new instance from AWS. To use this new capacity efficiently, pods are assigned to the node until its resources are considered fully allocated. A node can go from no applications running to being maxed out within moments of being ready to receive these applications. As we migrated more and more from our old container platform to our new container platform, we started seeing some concerning trends. Some nodes were stalling for long periods of time with a simple health check timing out after 30 seconds. An initial investigation showed that mount table length was increasing dramatically in these situations, and reading it alone could take upwards of 30 seconds. Looking at systemd's stack, it was clear that it was busy processing these mount events as well and could lead to complete system lockup. Kubelet was also timing out frequently, talking to containerd in this period. Examining the mount table made it clear that these mounts were related to container creation. The affected nodes were almost all R5 metal instances and were starting applications whose container image contained many layers, that is 50 plus. Challenge: Mount lock contention. The flame graph in Figure 1 clearly shows where containerd spent its time. Almost all of the time is spent trying to grab a kernel level lock as part of various mount related activities when assembling the container's root file system. Okay, here we see root at the bottom and then containerd. And then this has various runtime related operations. Hmm. And here at the top, we do see some lock related functions, which they are probably talking about. Looking closer, containerd executes the following calls for each layer if using user's namespace. Open tree to get a reference to the layer or directory. Mount set attribute to set the ID map to match container's user range, shifting the ownership so this container can access files. Move mount to create a bind mount on the host with this new ID map applied. These bind mounts are owned by container's user range and are then used in the lower DIRs to contain the overlay FS based root file system for the container. Once overlay FS root file system is mounted, the bind mounts are then unmounted since they are not necessary to keep around once overlay FS is constructed. If a node is starting many containers at once, every CPU ends up busy trying to execute these mounts and U mounts. The kernel VFS has various global locks related to the mount table, and each of these mounts requires taking that lock, as we can see in the top of the flame graph. Any system trying to quickly set up many containers is prone to this, and this is a function of the number of layers in the container image. For example, assume a node is starting 100 containers, each with 50 layers in its image. Each container will need 50 bind mounts to do the ID map for each layer. The container's overlay FS mount will be created using those bind mounts in the lower directories, and then all 50 bind mounts can be cleaned up via umount. Container D usually goes through this process twice, once to determine some user information in the image, once to create the actual root FS. This means the total number of mount operations on the startup path for our 100 containers is 100 into 2 into 1 plus 50 plus 50, which is 20,200 mounts, all of which require grabbing various global mount related locks. Hmm. Global mount related locks, which are probably at the node level, which is scheduling all these 100 containers. Diagnosis. What's different in the new runtime? Okay, so they mentioned that they moved from their own container orchestrator platform to AWS, which actually caused this issue. So now they're looking into what is different in the new runtime. As alluded to in the introduction, Netflix has been undergoing a modernization of its container runtime. In the past, a virtual kubelet plus Docker solution was used, whereas now a kubelet plus container D solution is being used. Both old runtime and new runtime used user namespaces. So, what's the difference here? Old runtime. All containers shared a single host user range. UIDs in the image layers were shifted at untar time, so file permissions matched when containers accessed files. This worked because all containers used the same host user. New runtime. Each container gets a unique host user range, improving security. If a container escapes, it can only affect its old file system. To avoid the costly process of untarring and shifting UIDs for every container, the new runtime uses the kernel's ID map feature. This allows efficient UID mapping per container without copying or changing file ownership, which is why Container D performs many mounts. Figure 2 below is a simplified example of how this ID map feature would look like. Okay, so layer 1 with owner UID 0, which has a ID map of 100,000. Okay, so here basically owner UID to ID map mapping is stored. Why does instance type matter? As noted earlier, the issue was predominantly occurring on R5 metal instances. Once we identified the root cause, we could easily reproduce by creating a container image with many layers and sending hundreds of workloads using the image to test the node. To better understand why this bottleneck was profound on some instances compared to the others, we benchmarked container launchers on different AWS instance types. R5 Metal, which is 5th gen Intel, dual socket, multiple NUMA domains. M7i Metal 24XL, 7th gen Intel, single socket, single NUMA domain. M7A 24 extra large, 7th gen AMD, single socket, single NUMA domain. Baseline results. Figure 3 shows the baseline results from scaling container and each instance type. Okay, so there are a number of containers on the x-axis and elapsed time in seconds on the y. At low concurrency, that is less than 20 containers, all platforms perform similarly. As concurrency increases, R5 metal begins to fail around 100 containers. 7th generation AWS instances maintained lower launch times and higher success rates as the concurrency grew. M7A instances showed the most consistent scaling behavior with the lowest failure rates, even at high concurrency. Deep dive. Using perf record and custom micro benchmarks, we can see the hottest code path was the Linux kernel's virtual file system, VFS, path lookup code. Specifically, a tight spin loop waiting on a sequence log in the path init. The CPU spent most of its time executing the pause instruction, indicating many threads were spinning, waiting for the global log, as shown in the disassembly snippet below. Using Intel's top down microarchitecture analysis, DMA, we observed 95.5% of the pipeline slots were stalled on contested accesses, TMA contested accesses. 57% of the slots were due to false sharing, multiple cores accessing the same cache line. Cache line bouncing and log contention were primary culprits. Given high amounts of time being spent on contested accesses, the natural thinking from the perspective of hardware variations led to investigation of NUMA and hyperthreading impact coming from the architecture to this subset. NUMA effects. Non-uniform memory access, NUMA, is a system design where each processor has its own local memory for faster access but relies on an interconnect to access the memory attached to a remote processor. Introduced in the 1990s to improve scalability in multiprocessor systems, NUMA boosts performance but also introduces higher latency when a CPU needs to access memory attached to another processor. Figure 4 is a simple image describing local versus remote access patterns of a NUMA architecture. Hmm. AWS instances come in a variety of shapes and sizes. To obtain the largest core count, we tested the two socket 5th gen middle instances, R5 metal, on which the containers were orchestrated by the Titus agent. Modern dual socket architectures implement NUMA design, leading to faster local but higher remote access latencies. Although the container orchestration can maintain locality, global locks can easily run into high latency effects due to remote synchronization. In order to test the impact of NUMA, we tested on AWS 48XL size instances with two NUMA nodes or sockets versus an AWS 24XL size instances which represents a single NUMA node or socket, as seen from the figure 5. The extra hop introduces high latencies and hence failures very quickly. Hyperthreading effects. Hyperthreading, HT. Disabling HT on M7i Metal 24XL Intel improved container launch latencies by 20 to 30%, as seen in the figure 6. Since hyperthreads compete for shared execution resources, worsening the lock contention. When hyperthreading is enabled, each physical CPU core is split into two logical CPUs, hyperthreads, that share most of the core's execution resources, such as caches, execution units, memory bandwidth. While this can improve the throughput for the workloads that are not fully utilizing the core, It introduces significant challenges for workloads that rely heavily on global locks. By disabling hyperthreading, each thread runs its own physical core, eliminating this competition for shared resources between hyperthreads. As a result, the thread can acquire and release global locks more quickly, reducing overall contention and improving latency for operations that are generally shared underlying the underlying resources. How does hardware architecture matter? Centralized cache architectures. Some modern CPU server CPUs use a mesh style interconnect to link the cores and cache slices, with each intersection managing cache coherence for a subset of memory addresses. In these designs, all communication passes through the central queuing architecture, which can only handle one request for a given address at a time. When a global lock like the Mount lock is under heavy contention, all atomic operations targeting that lock are funneled through this single queue, causing requests to pile up and resulting in memory stalls and latency spikes. In some well known mesh based architectures, as shown in the figure 7 below, there's a central queue called the Table of Requests, TOR, and it can become a surprising bottleneck when many threads are fighting for the same lock. If you've ever wondered why certain CPUs seem to push for breath under heavy contention, this is often the culprit. Distributed cache architectures. Some modern server CPUs use a distributed chiplet based architecture, figure 8, where multiple core complexes, each with their own local loss level cache, are connected via a high speed interconnect fabric. In these designs, cache coherence is managed within each core complex, and traffic between the complexes is handled by a scalable control fabric. Unlike mesh based architecture with centralized queuing structures, this distributed approach spreads the contention across multiple domains, making severe stalls from the global lock contention less likely. For those interested in the technical details, public documentation for major CPU vendors provides deeper insight into these distributed cache and chiplet designs. Here's a comparison of the same workload run on M7i centralized cache architecture versus M7a distributed cache architecture. Note that in order to make it closely comparable, hyperthreading HT was disabled on M7i given previous regression seen in the figure 6, and experiments were run using same core counts. The results clearly show fairly consistent difference in the performance of approximately 20%, as shown in the figure 9. Micro benchmark results. To prove the above theory related to NUMA, HT, and microarchitecture, we developed a small micro benchmark which basically invokes a number of threads that then spin on a globally contended lock. Running the benchmark at increasing thread counts reveal the latency characteristic of the system under different scenarios. For example, figure 10 below is the micro benchmark results with NUMA, HD, and different microarchitectures. They have also attached the link to the micro benchmarking that they did. This is the GitHub repo for the same global log bench. This repository contains three C benchmarks for measuring spin lock contention and pause instruction behavior on multi-core system. Each benchmark is designed to highlight different aspects of cache contention and thread synchronization. Platform requirements. These benchmarks are designed and tested for Hmm. Okay. Got it. Results from this custom synthetic benchmark, which is pause benchmark, confirmed that on R5 metal, eliminating NUMA by only using a single socket significantly drops latency at high thread counts. On M7i metal 24XL, disabling hyperthreading further improves scaling. On M7a 24 extra large, performance scales the best, demonstrating that a distributed cache architecture handles cache line contention, in this case of global locks, more gracefully. Improving software architecture. While understanding the impacts of hardware architecture is important for assessing possible migrations, the root cause here is contention over a global lock. Working with Containerd upstream, we came with two possible solutions. Use the newer kernel mount API's fsconfig lower dir plus support to supply ID mapped lower dirs as FDs instead of file system pods. This avoids the move mount system call mentioned prior, which requires global locks to mount each layer to the mount table. Map the common parent directory of all the layers. This makes the number of mount operations go from ON to O1 per container, where N is the number of layers in the image. Since using the newer API requires using a new kernel, we opted to make the latter change to benefit more of the community. With that in place, no longer do we see the Containerd's flame graph being dominated by mount related operations. In fact, we see in figure 11 below, we had to highlight them in the purple below to see them all. Hmm. Okay, so the mount related operations, which basically covered the entire graph, and the flame graph that they mentioned, like in the beginning of the article, is now just a tiny portion of it, which is a significant improvement. Conclusion. Our journey migrating to a modern kubelet plus Containerd runtime at Netflix revealed just how much deeply intertwined software and hardware architecture can be when operating at scale. Indeed, while kubelet and Container's use of unique container users brought significant security gains, it also surfaced new bottlenecks rooted in container and CPU architecture, particularly when launching hundreds of many layered container images in parallel. Our investigation highlighted that not all hardware is created equal for this workload. Centralized cache management amplified the cache contention, while distributed cache design smoothly scaled under load. Ultimately, the best solution combined hardware awareness with software improvements. For an immediate mitigation, we chose to route these workloads to CPU architectures that scale better under these conditions. By changing the software design to minimize per layer mount operations, we eliminate the global log as a launch time bottleneck, unlocking faster, more reliable scaling regardless of the underlying CPU architecture. This experience underscores the importance of holistic performance engineering. Understanding and optimizing both software stack and the hardware it runs on is a key to delivering seamless user experiences at Netflix scale. We trust these insights will assist others in navigating the evolving container ecosystem, transforming potential challenges into opportunity for building robust, high performance platforms.